Thank you very much for your introduction. So I suppose good morning or good evening for everybody. So my presentation will be around a paper that has been presented at ISTTT in August in Kobe, Japan. And the main topic is, I don't know if you can all see like the presentation in full screen. So the main topic of the paper and the work was actually the characterization of network traffic processes under an adaptive control systems. So just a quick summary of what I'm going to present to you. So I will start with the description of the objective of the research, then the background, of course, the comparison with the state of the art. Then I will list the original contributions of the paper of the research. Then I will present to you in more detail what actually was presented at the conference. Then all of this research has been tested on a real data set, specifically in Dublin, where the SCATS control system is actually working. Then I will jump out to the conclusion. So the aim of the research that we have conducted is actually to provide sort of evidence of the traffic dynamics on a network level when an adaptive control system is working. So as we all know, adaptive control systems are dynamic. They are of course adaptive. Usually they have a large parameter space, and usually each one of these parameters has an effect on the control strategy and on the output of the control strategy. So our goal is to provide a data-driven approach, so some data-driven insights about how the control system is actually working and about the traffic, I would say the traffic state and its evolution on a network level. Differently from previous work, our dataset is based on data regarding the supply side of the control process. So specifically, we don't work on I would say the classic traffic variables. So let's say flow, density, and speed, because we don't have access to this kind of information. So most of the literature is actually focused on these three quantities, and most of the literature works on an estimation of the demand, and then an estimation of the, let's say, the required supply. So our dataset is a dataset collected by the SCATS system. It is an adaptive control system working in Dublin. So the traffic parameters that were collected by the control system are the degree of saturation, the flow, and the cycle length, and other control parameters. I will go deeper in detail of these three quantities later. So what it is very important is that these traffic variables are not measured in stationary conditions. So the sensors are very close to the stop line. And then what it is also very important is that we don't have any information about, I would say, the demand of traffic. So we have just a picture of the supply side. And we want to use this picture to infer when there are, I would say, misconfiguration of demand and supply, and when the traffic control system is actually causing queues, and how these queues spread over the network. So the original contributions of the research are three. So first of all, we characterize the dynamics of the arterial networks, and we take into account both the demand and the control side of the problem. Then one of the main insights from this characterization was the identification of a transient state that can be attributed to network effect. Then we also developed a network transition model used to establish and, of course, model the network relationships. So a network transition model that is able to tell you how the queues and congestions will propagate through the network. So first of all, we proposed a state classification model. So just let me give you an introduction about the quantities that are collected by the control system. So first of all, we have the degree of saturation that you can see here on the x-axis. So the degree of saturation is a kind of an non-dimensional quantity, and it measures how, I would say, how efficient the green time is being used during the last cycle length. On the other side, the control system also collect data of flow as vehicle per hour. So what happens is that the sensors in the Dublin city are placed very close to the traffic lights, and they collect data at each cycle length. So at each cycle length, at the end of each cycle length actually, we have a measure of the degree of saturation as a measure of how efficiency the last green time has been used, and also the flow, so how many vehicles the traffic lights has served during the last green time. So the SCATS control system in its present form is mainly, I would say, focused on how the degree of saturation works. So the system is designed as to recognize that there is a congestion, so an oversaturated condition, if the degree of saturation is higher than 100. So what we have found is, first of all, that there can be also some problems when the degree of saturation is lower than 100, and also that can be some cases when the degree of saturation is higher than 100, but actually the system is working well. So we analyzed the diagram between the flow and the degree of saturation at each of the intersection, and we have detected 3 states. So the first one is the free flow, the one that you can see in the picture with green color. So the free flow is describe a state that corresponds essentially to undersaturated condition. So in this case, undersaturated and also saturated condition. So in this case, what happens is that the traffic lights is serving as many vehicles as it can. So the system is working quite well, and there are no residual queues on that specific approach. Then there is a congested regime that you can see on the right of the diagram, where the flow goes very fast to 0 as the degree of saturation increases. So in this case, the congestion is severe, and the entire urban network is in oversaturated condition. So there are queues that are forming and that are not served. So what happens is that these queues are propagating backward through the network and are causing the stuck of the network. Then there is another state that we observed and that we discovered, that is actually one of the main sites of the research, is that there is a state where the degree of saturation is lower than 100, so when the traffic is supposed to be okay, but it's not, because the flow that is observed in those cases is actually lower than the flow that would be expected. So in the picture you can see this state with black color, and what it is important in this state is that you have actually a loss of capacity. So instead of being, let's say, in the green state, the flow is actually lower, so you have a loss of capacity. And we also evaluated in our research the amount of the loss of capacity that you can have, and how this can be detrimental on a network perspective. So just to give you an idea of how these states can be defined on a detector level, so very specific level. So here there are 3 examples of the signature, of the magnetic signature of the detector in each one of these states. So in the free flow state, you can see that the signature of the detector show the passing of vehicles, and the vehicles are going freely, so there is no problem regarding possible queues. Of course, during red time, vehicles are stopped. Then there is the underutilization case, in which for a first part of the green time, the vehicles are going freely, but then they get stuck. So the green time is not fully exploited because there is a congestion. The congestion is not severe yet, but there is a congestion that need to be detected and need to be solved. Then there is the third state, that is the congestion one. In this state, the vehicles are not going freely, so they are actually waiting. They're going very slowly over the detector. So in this case, you have a residual queue, and the congestion is very severe. So if you look at the time series of, in this case, of a day in April 2013, you can observe that we can get quite few insights from this classification of traffic. So these two pictures represent the degree of saturation and the flow during all the day. So the first thing that we want to I want to say is that so in the diagram on the top, there is a line that shows to you the target level of SCATS. That it means where SCATS think that that everything is going well. So where SCATS I would say try to push the traffic to be, okay? So above this line for SCATS there is congestion. Under this line the conditions are fine. So the first thing that we can observe is that if you look at the circle number with the number 2, what we can see as first of all is that the system works well even if the degree of saturation is high. So higher flow can be served in these cases. So in this case, SCATS will say that the traffic is oversaturated, but this is not true, because if you see at the flow is actually going, so the traffic is not stuck. On the other hand, if you look at in the other part of the diagram where the number 1 is put, in this case the states underutilized or C are actually observed, and in this case where it is evident is that there is a decrease in the flow. So a decrease in the flow is actually the way to recognize that the system is not working properly. I would say an unexpected decreasing of flow is the way to recognize that the system is not working properly. As I anticipated to you before, we also define a capacity loss. So in case of a use state is observed, we define a capacity loss that is the amount of flow that should have been served by the traffic light if the traffic light was in normal condition, so in undersaturated condition, but that has not been served. So let's say the capacity loss is kind of missed service rate. Okay, so the capacity loss is very important because it gives you an idea of how many vehicles are not served by the traffic light. So how many vehicles will remain in the queue of the traffic light not being served. So what it is very important also in this research is that we also build a network model in order to define how these 3 traffic states will propagate through the network, and in order to define if let's say to develop a method to identify most frequent patterns of backpropagation of congestion and the most frequent route of congestion. So we use a dynamic Bayesian network to model the spatiotemporal evolution of the traffic states. Each node of the Bayesian network is a traffic sensor, and the nodes of the Bayesian network are connected following the backpropagation of traffic, the possible backpropagation of queues. So we use the likelihoods to find the most frequent routes of congestion. Sorry. And we used all the data actually to train the dynamic Bayesian network, and I will show you now the results on real data, both of the classification method and also of the network model. So the data set is a data set of Dublin. So the method that I just presented to you has been evaluated on data collected by SCATS, the control system in Dublin. So loop sensors are located at the very stop line. So they are located very, very close to the traffic light. And this is the reason that the data collected cannot be considered as stationary. And this is one of the issues that you have to take into account when you analyze those data. And this is one of the reasons that the classical approaches can't be used. Then this data collect the traffic parameters at every cycle length. Usually the cycle length can be very, very, I would say, spread. But usually the cycle length is around 2 or 3 minutes. So these sensors collect flow as a normal counting of vehicles that are served during the green time. Then the degree of saturation, that it's a unitless measure of how efficient the green time has been used during the last cycle length. So in theory, if we have a degree of saturation lower than 100, so if the degree of saturation is equal to 100, then it means that the traffic light is working at the saturation level. Then if the degree of saturation is lower than 100, it means that the system is working at other undersaturated condition. Then if the degree of saturation is higher than 100, it means that the system is in oversaturated condition. We proposed an approach a bit more, I would say, complex and evolved compared to this one. So we used both the degree of saturation and the flow to detect the state. So we detect the free flow, the underutilization state, and the congested state. And then we also have other control parameters that are collected by the system. So there is the green time and the cycle time. So all of these control parameters are actually a picture of the control strategy of the system and a picture of how the system is working. So the data that we have analyzed are collected over the period from February to May 2013. And we have focused our attention in the city center. So we have more or less 125 sensors in the city center. So this is the picture of the traffic monitoring system over all the city. So as you can see, the sensors are pretty spread out over the city and they are located over the major intersections of the city. Of course, the city center is the area where we have more intersections that are monitored. We focused on the square that there are in the picture, and we focused particularly on this set of sensors in order to evaluate our approach, to validate our approach, and to understand which will be the effect of our approach on a real system. So this is an example of the classification system over in a specific instant of time. So in this case, the data are from the 10th of May 2013. And this picture is taken from the afternoon, from a specific time in the afternoon, 5:40 more or less p.m. So as you can see from the picture, the traffic, of course, is quite congested, and but actually there are some sensors that are in free flow. So what it is very important here is that we have to understand when we design a control system how we can exploit the free flow sensors in order to decrease the congestion or decrease at least the load from the underutilized and congested sensors. So regarding the network level analysis, we have used the dynamic Bayesian network that I presented to you in one of the slides. So in this case, we have used that dynamic Bayesian network to identify the critical backpropagation path of queues in the network. So what happens here is that in this picture, I show the two most frequent backpropagation paths of queues, of congestions. But what it is very important here is that there is this point circled by red, and this point has been recognized as a frequent route of spillovers. And what it is interesting is that this point is actually a point where the traffic is very, very. So if you go there, like on the streets, and you look at the traffic conditions there, what happens is that in that particular point, the bus lane is always very, very congested. So the bus tended to overcome over each other and to invade the lane of cars. So this is actually in real world a spot where there is the route of spillovers, because there is always congestion and the cars can't get through easily. This is something that the method discovered completely, of course, automatically. So if we look to the capacity loss over the critical path that I just showed you, so these three pictures shown the capacity loss in percentage, so in percentage over the expected flow of the C state and the U state. So the C state is in red, the U state is in black. So what it is, I would say, pretty interesting here is that neither the C state and the U state are actually more critical than the other one. So we can't say from this diagram that the U state is less critical than the C state or vice versa, because there are cases where the loss from the U state is higher and cases where the loss from C state is higher. So even if the U state does not describe a so critical condition and severe condition and as the C state, at the end of the day, the capacity loss that you can that the traffic experiment, the traffic sense in U state and C state is actually quite similar. So the U state is as much important as the C state in terms of the residual queue that can't be served and the effect, the detrimental effect on a network level. So this picture show the capacity loss on a sort of heat map. So on the x-axis there are time, and on the y-axis there are the various intersections that we are analyzing. So in this case, for example, so the plot on the top of the slide show the capacity loss computed when only the C state is considered. On the bottom we have the capacity loss computed when both the U state and the C state are considered. As you can see, the ability of the model that we have developed to recognize the use state as well as a congestion or as a problematic state is pretty useful, because we can take into account a capacity loss that otherwise would be undetected, that is as much as 20% of the unused capacity. So the ability to identify the use state is quite important in this sense. So in this case, in this picture, we have shown the traffic state in a specific case where the coordinated control is not actually doing, I can say, the best that it can. So so let's start from the beginning. So in this picture, first of all, there is a spillover that is detected, that you can see that is marked with the red arrow. So this spillover is backpropagating from north to the south of this area, and it is affecting this little sensor or approach circled by the black circle. So what it happens in this case is that the control system will try to give more green time to that approach circled by black. But what happens is that this green time is going to be wasted because there is a spillover. So even if we give a lot of green time to that approach, this green time is not going to be used because the traffic is stuck. So the main, I would say, insight from this example is that there are other competitive approaches that are marked here with yellow arrows that could have used the green time much more efficiently than the other approach. So if we had given more green time to these approaches, this green time would have been actually used. And so this is an example to show the waste of green time that can happen if the wrong control strategy is actually deployed. So we run also some experiments around the macroscopic analysis of our method. So given the fact that we don't have any access to information about the occupancy at the speed of vehicles, we have tried to give, so we can't use, let's say, the fundamental diagram, okay, so this for sure, but our aim was try to give a description of the network of a macroscopic side, even if we didn't have access to the classical traffic variables. So as a descriptor of the entire network that we are analyzing, we have defined the relationship between the network level wide loss and the network throughput. So in this case, the loss is computed as using the function the formulas that I described to you before, and it is actually an average loss. Then the total network throughput is the average throughput of all the sensors at the border of the networks. So what it is pretty interesting here is that even if we don't have a measure of occupancy and speed, so even if we don't have a measure of density, we have a shape, I would say, of the plot that is very close to a fundamental diagram. So in this case, the whole network never gets completely stuck, so we don't have very, very congested state of the overall network. So this is the reason that the diagram is kind of not complete. But at the same time, this is a very good insight from the network that we can actually give a macroscopic, I would say, descriptor of the network, even if we don't have the density or the speed measurement. So in the other picture on the right, we have all the network throughput of the network, and in this case the network throughput has a pretty, I would say, classical behavior. So we can see that there are the very common descriptor of traffic. So this is so in the paper there are just these two preliminary results on this level, but we are working more in detail to understand more how to give a description of the entire network on a macroscopic level. Sorry, I can't hear you. I can't.
Might be just some background noise. You may just go ahead.
Okay.
Proceed. Let me try to do that.
Okay, so this is essentially what we have done during our research. And so this is a slide that contains the main conclusions of the work. So the method that we have proposed has been proved on real data to provide some important and relevant insight on the effect of the U state and the C state, and the difference between these two states, and how these two states propagate through the network. So in this form, the classification model is designed around the SCATS system because this was the data that we had. But similar data-driven approaches can be considered even if we have other kind of sensors. I would say it is just a matter of customize the developed algorithm to the specific data, but it's fine. It would be fine. Then another important thing is that we have started working the impact of the spatial heterogeneity of congestion on throughput with the macroscopic analysis that we have done. But in this case, we are still going on, so this is one of the future work. So we are considering a higher number of control parameters in order to have a more complete description of yeah, let's say on the impact of this congestion on a network level. So thank you for listening. So if you have any question, just ask me.
Thank you, Dr. Pascale. And for everyone, if you have questions, you can either speak out from your microphone or you can type out the questions through the chat box. And I think I've received a couple of questions in the middle of the presentation by Kevi Faroki.
Okay, so yeah, I see the question as well. So it really depends, because it depends on how far the intersections are. But in our case, it could be from 200 meters to 500 meters, more or less. But if you have intersections that are more far than 1 kilometer, you will have 1 kilometer as well. Okay, so for sure, the value of the probe data will be to validate, I would say, the propagation of congestion. So we could, yeah, so it would be another way to validate if the propagation of congestion is actually going in the right direction, in the direction that is estimated from the method, yeah. You are very welcome. Thank you very much.
we should have plenty of time for entertaining questions, and we have a great audience today, and I encourage you all to,
Can I ask a question, please?
Yes, of course. Go ahead.
Yeah. So, Alessandra, thank you for this interesting presentation. It's Jacques Haddad from Technion. I just didn't follow you regarding the degree of saturation. So can you explain me again how you mathematically calculate the degree of saturation?
Okay.
I mean, so I'll give you the degree of saturation, and the follow-up question will be, maybe will not be. It's related to how you can get degree of saturation, which is more than 100%.
Okay, so the degree of saturation is a measure internal to the control system. So we didn't, I would say, compute it, but it is an output of the monitoring system.
I understand, but theoretically, how it should be computed?
So theoretically, is the ratio between the demand and the supply. Okay, so if the demand is lower than the supply, that is what you actually want, then the system is in undersaturated condition. If the demand is higher than the supply, then you are in oversaturated condition because the supply can't serve the demand. Is a ratio, okay?
Hello, this is Alex Stevanovic from Florida Atlantic University. Can I jump in this discussion? Maybe I can offer a slightly better explanation how SCATS does calculate the degree of saturation. And correct me if I'm wrong, but I think you are using a SCATS degree of saturation for this measure. It is not necessarily the full physical capacity as we would capacity is not the right word, but not really a full physical degree of saturation where everything to the maximal amount is accounted. It's more like a degree of saturation of 1 or 100% is set at some reasonable rate based on a formula which is beyond the scope of this conversation. They essentially measure time and space that the detectors near the stop line are occupied by cars, and that value of 100% is not physically what is going to be the maximum value. So SCATS is able actually to report degrees of saturation that go probably all the way up to 1.3 or 130% or so, maybe even slightly more. It will depend on what you calibrate as the point where you have 100% occupation of your detector, and that is something that can be calibrated within SCATS. So I hope that clarifies a little bit of how this degree of saturation is calculated and why the values are higher than 100%.
Yeah, thank you very much for your explanation. More or less it is like that, yeah. There are some other parameters underneath, but more or less, yeah.
Okay, then Alexandra, the follow-up question will be, can you back to this nice triangular shape, almost triangular shape,
yep.
Second slide of the third slide with the real data? I mean,
like this one?
Yes, that one. Yeah. So you distinguish here between the, let's see, 3 regimes like free, C, and U. I'm just wonder how, for example, inside this triangular, how you can distinguish between the green and how you can classify between the green and the underutilized, so the free flow and the underutilized points. And the second question would be, I see a very high scatter points in the uncongested regime, and you explain why you have points, loss of capacity, where is black points, but I don't understand why you don't also have a high scatter of points in the congested regime under the red congestion regime. I mean, I understand that these these variables are different than density and flow and so on, but a little bit of, you know, we expect again some points in the more scatter points in the congestion regime. So can you have some explanation for first how you classify, and second about the scatter?
Yeah. Okay. So the answer to the first question is the following. So let me just open one picture. Okay. Can you all see that?
Yeah.
Okay. Okay. So what happens here is that so on the top right there is the diagram, the triangular one. On the bottom there is a sort of I would say diagram of the capacity, like the service rate of the traffic of the specific traffic light in this case. So what we have done is that we have so of course it is an approximation. What we have tried to approximate the green area with a kind of a Gaussian, okay? So then this limit is correspond to twice the standard deviation, okay? Then this is the answer to your first question. Of course, this is an approximation. Yes, this is what we have done. So first of all, we have estimated the expected service rate, and then we have estimated how this service rate can change, so the standard deviation, and then we have put a threshold on the standard deviation. Then regarding the second question, okay, so how SCATS compute the degree of saturation is quite tricky. So there are a lot of different parameters that are calibrated underneath this number. So what happens in the congested state and the black one? So the fact that there is that kind of triangle that is completely white, okay? So what happens here is that, so I don't have any picture here about the temporal evolution of the state, but what happens here is that each time that the system is in oversaturated condition, so the degree of saturation is higher than 100, SCATS tries to meet is, I would say, objective, that is maintain the degree of saturation around 90. So it increases the green time, and then that point from the red part move to the black one. Okay. The problem is that the point moves, but the flow remains the same. So what happens is that the points are continuously jumping from one state to another one, okay, but the flow is not increasing. So it is a kind of, in this kind of cases, the system is kind of trapped in congestion, and SCATS tries to recover, but it can't. Okay, so the reason that you have this white triangle is an effect of the control strategy. So of the fact that SCATS is trying to, so at each cycle is trying to maintain the degree of saturation lower. Okay, so it is, I would say, partly an effect of the control system.
Okay, thank you for your answer.
Okay, you're welcome.
Any other questions?
This is Alex Stevanovic. Alexandra, your latest statement. I'm just thinking, looking at this chart and thinking, if we were going to represent this data by the curve of the fundamental diagram, I'm not even 100% sure this would be the same curve. These would probably be different curves, as is your capacity changes when SCATS, let's say, increases cycle length. So degree of saturation jumps, increases cycle length, capacity is changed, then wouldn't that be like a different curve on your fundamental diagram?
Yeah. So I agree with you. This is something. So this is the reason in one of the conclusions we have written that we are currently related that diagram to all the parameters. Okay. Yeah, you're right. That were just a preliminary analysis about that.
Okay.
Yeah, you're right.
Thank you.
Yeah, we are working on that.
So, Alessandra,
yeah,
maybe I can ask one question if it's fine. So I understand the Bayesian network. Okay. All right.
Mute all.
Mute all. Hi. So let's see. Alessandra, can you hear me now?
Yeah.
Okay, great. So I understand you use the Bayesian network and this data-based models to analyze the data. It's a smart way of doing that. It's great. So I wonder, you're talking about spillback, and that has to do with the queuing model and some kind of classic traffic flow model in the physical realm. So would it be possible to integrating some of those physical roles into your Bayesian network model so you can sort of harvest the advantages from not only the power from the data-driven methods, but also the physical models underlying in this system?
Yeah, I would say yes. That is for sure one of the things that we can explore. Yeah. So like to make the model not so data-driven as it is now, but to put some a priori information about the traffic model. Yes. That is for sure something that can be done. Yeah. It's one of our I would say ideas to improve it.
All right, great.
Yeah, Alessandra, one more question.
Yeah.
I want why you don't. I mean, you have magnetic loop detectors, right? Why you don't? You have an access for regular, traditional, let's say, not regular data of occupancy and density.
Nope.
Sorry, occupancy and flow. No.
No, we don't have. We have access. So how can I say it? So we have access only to the data after the data are processed by SCATS. So we don't have access to the raw one.
Okay. So you don't have any option to compare this nice triangle with traditional.
Yeah, I know. So this is something that it would be very, very nice. But we have tried, but we don't have access to those data. No, that would be very, very nice. Yeah, I know. It's gonna be very useful, but we don't have access to even we don't have access to the magnetic signature. Okay, so nope.
But this is something that could be done potentially in simulation, where you could get SCATS data from stop line detectors and then just set up some of the upstream detectors to measure.
Yeah. So actually, we have tried to do it a little bit. The problem is that. The problem is that you have, so if you simulate a network, so first of all, you can simulate all the control strategies that the SCATS system can put in place, and the second.
Why not? But go ahead. Okay, go to the second. Yeah.
Okay, because it is a proprietary system, and it is very hard to find a very, very detailed documentation about it. Okay, so let's put it this way.
Okay, contact me after the presentation.
Okay.
I want also to contact you after the presentation.
Okay, but then the other thing would be that we would need to, I would say, not to simulate a simple network, but a complex one. So we would need a bit of time for that. Yeah, but it is for sure something that can be done. We have thought about it. We haven't done it yet, but yeah.
Okay.
Okay, any other questions? Okay, great. Well, again, thank Dr. Pascale for her great presentation and very insightful work, and thank all of you for coming here and having a great discussion on this topic. So the next presentation in this webinar series will be on next Friday, 10 a.m., and that'll be the last of this year. And with this, I hope you all have a great weekend. Thank you all, and the meeting adjourns.